Hello again, Year 9. At this point, you should have already corrected your homework from last week, which was on the chemistry topic. Okay, and that was the one all about isotopes and ions and numbers of protons and electrons. Now, this week, new work is going to be on the first physics topic for GCSE. All right, so we've already done the first biology topic and the first chemistry topic, so we've already done loads of work, which is great because it puts us in a fantastic position for the start of next year. All right, and now we're going to do our physics topic. And you might be looking at this and thinking, the particle model, haven't we already done that? And you're completely right, we have already done this. Right, so we've done it from a chemistry perspective. But one of the things that you'll find, especially at GCSE, is that different kinds of scientists have different ways of thinking about things and different ways of looking at things. All right, so you'll do the particle model from the chemistry point of view, and you'll do the particle model from the physics point of view, and they're slightly different. All right, but they help each other out. So, same as normal, you should have already done your 10-question quiz, you're marking the homework, you've got no distractions, you can print this out if you want, or you can just follow along and answer the questions in your book at the end, making notes in your book as well. This is all the information, all the key bits of information that will come through, which will come across as we go through this. And you can use the usual method to help you remember that. So, section 1, the particle model. All right, now, amazingly, this allows us to learn a little bit of history. So you might know that my favourite subject is maths, which is just beats chemistry. But one of my other favourite subjects is history. And in fact, when I did my A-levels, I did maths, chemistry, and history. So this is a real treat for me. Okay, so we have already covered some of the basic science behind the particle model in the chemistry unit. Good. Now, if we think back, the idea of an atom goes back more than 2,000 years to the ancient Greek philosophers. Now, in Greek, atomos, now I don't speak Greek, so I hope I'm pronouncing that correctly, means indivisible. So this word atom comes from atomos, which means that something is indivisible, that can't be divided. And Greek philosophers thought that an atom was what you would end up with if you kept breaking matter into smaller pieces for as long as you could. So let's imagine if I take my ruler and I snap it in half, and then I snap that half in half, and I snap that a quarter into a half, and I keep doing that until I can't do it anymore, and I get these tiny, tiny pieces. They thought that was an atom. Okay, now, that wasn't right, but it was a good idea. Now, interestingly, we didn't make much progress on this idea for a long time. So this is about 2,000 years ago. And then in the 1870s, so only about 150 years ago, a man called John Dalton, he established that all atoms in an element are the same. Okay, now you'll know that because you'll remember when we did the chemistry topic, I said, think about a piece of gold. Piece of gold. Now, a piece of gold has only got one type of atom in it. All right? And that atom is gold atoms. So if I give you a lump of gold, which is unlikely to happen, I'm afraid, but if I give you a lump of gold, all of the atoms would be gold atoms in there. Okay? And that is what an element is. He also said that atoms in one element are different from the atoms in all other elements. And you'll remember that we said in chemistry that if you've got 6 protons, it must be carbon. If you change the number of protons, let's say I increase the number of protons by 1 to get 7, I don't have carbon with 7 protons. I have a different element. I have nitrogen. Okay? And in chemical reactions, atoms are combined, separated, or rearranged. And you'll remember we had this idea of if you have, let's say, methane, CH4, plus oxygen, you make carbon dioxide and water. That's that. So the atoms stay the same. There's the same number of atoms on each side, but they get rearranged to make new things, okay? And you'll remember that the definition of a chemical reaction is where a new substance is made. So, John Dalton, okay, I know we're in the physics part of the course, but John Dalton, basically a chemist, all right, did lots of cool chemistry stuff. Now, in 1897, so about 30 years after John Dalton, a man called J.J. Thomson discovered the existence of the electron. Okay, so John Dalton didn't know about any of these subatomic particles, he just knew about atoms. Now, J.J. Thomson discovered the existence of the electron, a type of particle smaller than an atom with a negative charge. To explain this, he proposed something called the plum pudding model of the atom. Now, a plum pudding it's like a Christmas pudding. Okay, so just imagine a Christmas pudding. Now, I'm not going to draw it like a Christmas pudding. I'm going to draw it just as a big circle. Okay. All right. So, in a Christmas pudding, what you've got is you've got lots of fruit. You know, lots of raisins and currants, or you know, bits of maybe I don't know what else they put in them, stuck into the plum pudding. Okay, and he thought that an atom was like this, but instead of having this cake, what you've got is a cloud of positive charge, all right? And then just like the bits of fruit in a plum pudding or a Christmas pudding, what you had is bits of negative charge stuck into the cloud of positive charge. Okay, and these were the electrons. All right, so the plum pudding model of the atom is electrons in a cloud of positive charge. All right, now, fine, okay, it's a model, so it explained why you get particles smaller than an atom called an electron with a negative charge, but it's not necessarily correct. And a couple of years later, in 1899, Ernest Rutherford did a fascinating experiment that disproved the Thomson model of the atom. And when I say that this was a fascinating experiment, I really mean it. This is one of the, in my opinion, one of the great experiments of all time. Really tremendous work by Ernest Rutherford. So what he did was, he took a very, very thin piece of gold. Very, very thin. Okay, so this is, we're going to call it gold foil. All right. And around the piece of gold foil, he put a detector. Like this. Okay, so this is a detector. Now, why did he put a detector around the piece of gold foil? Because what he did, he had over here a piece of equipment that would shoot particles. All right. So this piece of equipment here fires alpha particles at the piece of gold foil. Okay. Now, these alpha particles, they're just small particles. I'll talk about those in a minute. And the gold foil is very, very, very thin. In fact, so thin, you know, it's only a few atoms thick. You know, incredibly, incredibly thin. All right. Now, what happened was, almost all of the particles, so he's firing these alpha particles at the gold foil, and you can see what happens to them. You know, so if a particle goes all the way through and hits here, he knows that it's gone straight through the gold foil. If the particle goes here and then comes up here, he knows it's been deflected. If the particle comes up here and he gets a signal here, he knows it's been deflected back towards where it came from. And what he found was that almost all of the particles went straight through the gold foil. So the biggest signal was here. Almost all of them go straight through. Almost all go straight through. And he thought to himself, that's interesting. Why, if I've got this piece of gold foil that is being fired through, why would all of them, almost all of them, go straight through? And he figured that it must be because gold atoms here must be mostly empty space. Because if you think about it, if the alpha particle goes straight through the gold foil, it means there must be nothing in its way to stop it or deflect it. And if there's nothing in its way, the atom must be mostly empty space. All right, so at this point he was probably thinking, well, Thomson's plum pudding model's not looking good now because that's not mostly empty space. It's got this big, it's got this positive charge stuff with these electrons stuck in it. All right. Now, so that was number one. The second thing he found was that the alpha particles come along and then some of them get deflected. All right. So number two, a small number are deflected. Okay. Now, at this point, I need to tell you something special about alpha particles. So an alpha particle is a proton, a neutron, another neutron, and another proton. That's an alpha particle. All right. It's actually the nucleus of a helium atom, but that's, you don't need to worry about that. It's just 2 protons and 2 neutrons stuck together. All right, which means that the overall charge is +2. All right, now, if you think about it, if some of these are deflected, what does that mean? Well, if the alpha particle is positive, it's going to be repelled by something else which is also positive. All right? Because remember that if the charges of 2 particles are the same, they will repel each other. So what he decided is that if I've got a positive particle coming in here and it is deflected by something in here must be positive. All right? So he decided that there must be a positive nucleus. All right, and so I can draw this now. Let's imagine you've got your alpha particle, okay, and that's coming along, and then your gold atom looks like this with the electron around the outside, okay, and this is positive. The alpha particle gets deflected by that. Okay, so that's what's happening. All right. Now, those are the first 2 observations he made. The third one was that he found, so almost all go straight through, a small number are deflected, and he found a tiny number, tiny number, 1 in 1,000 was deflected. Okay, a tiny number, not deflected, sorry, tiny number rebound back. All right, and he decided that what must be happening here is that rather than being deflected by the nucleus like here, they are hitting the nucleus full on and rebounding back. All right, and so he decided that the nucleus must contain most of the mass of the atom. Okay, and that makes sense because if the mass is mostly empty space, it means that most of the mass must be concentrated in this small nucleus, which these guys here hit, and it must be positive because it deflects these guys here. All right, so it's quite a complicated experiment, so I would recommend perhaps pausing the video while you make a few notes and watching the video again from the point where I talk about this. But the reason it's quite complicated is because it tells us so much fantastic information about the atom. Really, really impressive stuff for Rutherford to come up with this experiment. Okay, so the Rutherford model of the atom accounts for the small, dense, positive charge at the centre of an atom, as well as the fact that it is made largely of empty space. Now, you might think, well done, Rutherford, that's probably it. But no. In 1913, so about 15 years later, Niels Bohr developed the Bohr model of the atom. Now, Bohr suggested that electrons moved in fixed orbits called electron shells and do not spiral into the centre of the atom. All right, so what do I mean by that? Okay, it means that, now I haven't given myself any space to draw this picture, so I'm just going to draw it very small here. If you have the nucleus here, it means electrons are in orbits or shells around the nucleus. So, you know, let's say the cross is the electron, that's an electron, and then these guys are electrons, okay? And they orbit around the nucleus, a little bit like planets orbiting around the sun, okay? But you'll do more of that next year. That's really important in chemistry, actually. Now, although many improvements have been made to this theory over the past 100 years, it still serves as the foundation for our understanding of the structure of the atom. Okay, so the way we understand atoms now was established more than 100 years ago. Okay, so before we finish, I think it's important for us to just think a little bit about the people that are involved in this story. Okay, and the reason is because the development of the model of the atom is one of the greatest stories in modern science. Okay, it really is. The development that we made in our understanding of the world about 100 years ago is right up there as one of the great discoveries of modern times. Okay, it goes alongside things like the discovery of disease causes in things like cholera and antibacterial measures. But in terms of physics and chemistry, this idea of the atom was really amazing. Okay, and these are the four people that we've talked about today. And I just want to give you a little bit of information about them. So John Dalton was born in the Lake District up in the north of England. He was a Quaker, some of you might know about Bourneville, where the cabbage factory is. So that's a Quaker community, or you know, they were originally Quakers. And Quakers live very modest lives. They're very, very religious people, and they're not, you know, they're very devoted to what they do. J.J. Thomson was born in Manchester, so also a northerner. He was professor of physics at Cambridge from the age of about 30, and he won the Nobel Prize in Physics in 1906 for his work on the properties of electrons. All right, John Dalton didn't get a Nobel Prize. You know, maybe he would have done, but the Nobel Prizes didn't start being awarded until about 1900. All right, so he was a little bit too early. Ernest Rutherford was born about 20 years after Thomson in New Zealand. He also won the Nobel Prize. He won it in chemistry, and he later moved to the UK and worked in Manchester, actually. And Niels Bohr was a Danish scientist, and fascinating that he was awarded the Nobel Prize in Physics in 1922, and his son won the same award. So his son also won the Nobel Prize in Physics in the 1970s. Imagine the conversations at dinner time. You know, these two guys, both Nobel Prize winners. Anyway, so another thing about Niels Bohr is that he moved to the UK in 1943 to escape the Nazi occupation of mainland Europe, okay, because he was part of a Jewish family. So all fascinating characters that you can read about if you're interested. Now, homework, we've got 20 questions. All right, and I would like you to answer those in your books, please, and send me a picture on Firefly of the answers. All right, good work. I'll see you next week.